Okay, thank you. Okay. When you have an AI project in actually every domain, it's not only data scientists. Okay, so here we are the data scientists, but you have also other roles. So Alan is like, when you look in the AI project, he's the domain expert. He's the expert for the 5G network. And we work with Alan very tightly together in also what we will present over here. And you will see also here demos of the ML ops, okay, and the platform of the machine learning engineering, which is very tightly inside the AI project. What we are going to show over here, it's more for the data scientist parts over here, is all the conflict when you want to get into very good latency and performance versus the accuracy of the model, and how to get them both good, okay? And the use case that we will show is for NWDAF. So first a bit about the context where we worked. So Alan explained to you in general what is NWDAF in the 5G. In specific, what we will show over here, it's called a network function load prediction, where we have all kinds of metrics like CPU, memory, the load on the network function itself. It's like the middle layer that also we saw in the lecture of Osher, okay? And here we want to predict the next 10 points, where each point is every 15 minutes. Now, the thing is that we have quite a lot of load. In this case, we had 30,000 time series of such a data. And if we need to give a prediction to the next 15 minutes, we need to do it in total in 7 minutes. And actually, our main also competition and the market is all around how to do it in very low computing power, both in very tight in time, good accuracy, and very low computing power. Okay, so at least for such things, deep learning is out of the question. We will present here, I will start, and I will present to you a bit of a conceptual framework for assessment metrics for AI. Then Sagy, my colleague, will present to you tips and tricks. Okay. Oh, the screen sharing, okay. Yes, okay. Okay, so we can continue. Okay, thank you. Okay, so I will present assessment metrics framework. Presentation mode. You're not, just a second. Okay, now it's fine. They see it online, Olga, also fine? Presentation mode? Okay. Okay, then Sagy will continue with tips and tricks how to improve latency once you have already a model. And Boris will present more a pipeline solution, more architecture solution for a trade-off that enables you to select and fine-tune between accuracy and latency. So I'll start a bit with the framework, okay? Here you can see all kinds of measurements areas. You can see it? Okay, sorry for that. No, okay. Okay, so we see that there are measurements areas, okay? In the very basic days of the machine learning, we looked mainly on the model results. Actually, also competitions today mainly look on model results and less on other attributes. Where you have all kind of measurements like precision, RMSE, and so on. Here in our case, we took a map and we set some threshold that we don't want to pass it. Okay. The thing is, always put for yourself a threshold in the beginning of the project that is from a business perspective. Because otherwise, there is a tendency of the data scientist, we can have a better model and we would like to put the model to be better. But you don't always need it. And making a better model have a cost in performance, have a cost in computing power. Okay. Then also all kind of software have functionality demand. Okay. Some kind of functionality that you want your system to predict. So this is like every system that you have. But on top of it, now you have also performance and usability and effectiveness and even ethics, all kind of things like bias and fairness, okay, that Zev mentioned also in the compliance now of the Israel innovation. So for the performance, we have QPS, it's queries per second, okay, latency and throughput, which are all together connected. So actually you can select one or two of them and make the connections. So in our case, it was quite clear that we want a latency which is less than 7 minutes for the number of the time series altogether running. So that was our target. Now, when you look on where to test, where to examine your model performance, we need to look on the entire MLOps life cycle. So in the MLOps, we have actually 3 stages. Okay, we have the experiment, which is building the model, the first trial of the models and experimenting. We have the development, the part where we're actually bringing this into a product, making all the pipelines, connecting, making the things work, and then we have the operations. And there are things that you need to measure in every step. For example, if it's the accuracy of the model, then all of us know to split between a train and test and do the evaluation on the test data. And in the development, you always need also to keep testing that nothing harmed your results. So you need to keep all kinds of statistical tests. But in the operations, you need ongoing to monitor the results. When going now into the part of the performance, here in the experiment, we have the model latency, which we look in the experiment stage, we just measure, we do all kinds of tests only for the model, not connected to the entire product. Now, once we build the product, we need again to test it, but now it's entire product. And for sure, all the monitoring, like any other system that we monitor in performance, it's a regular IT monitoring for the performance. So now I hand the stage to Sagy, who will show us. Sagy will show us, if we look on this drawing, more the experiment part, the part of the data scientist, what the data scientists can do, even before we bring this into productization, how can improve the model running. Okay, then Boris will show us more in the part of the engineering, how we build pipelines that will help us for better performance.
Okay, thank you. So I want to talk about 4 tips and tricks, really concrete tricks we used in this specific use case for improving our performance. So the first and the most everyday is the vectorization. So working with data, we usually use tabular data or even images. Then it's very natural to work with vectors and matrices. And for this, we can use vector operations, and we have very great frameworks, NumPy and Pandas. We all, I assume, use. Which does this type of operations very fast. The thing is that these are implemented in C, and they have many optimization, and they do it very quick. So taking it one step further, then we want to utilize all our machine resources. So for this step, we can use parallelization. So we also have frameworks. We have Dask, we have Ray, Pandas Parallel. And we have the standard library of multi-processing. I'm talking about Python, by the way. I assume most of us are working in Python. So these are two techniques we used. So these are the more basic ones. But if we want to go to things that are a little bit more advanced, then also in this project we use the concept of just-in-time compilations. So in Python, this is an interpreted language. So of course, it takes time when we run our code. It takes time for the interpreter to convert our source code to machine code, and then to perform. Does it work? To perform the operations. So to deal with this overhead time, there is the idea of just-in-time compilation. The thing is that once our code is ran for the first time, then it is compiled, and the machine code version is cached. And then when we call our code again, then the cached version, the machine code version is used, and our code becomes much faster. So in Python, we have Numba, which is the just-in-time compiler. It requires some designing of the code. We need to use homogeneous type, and there are some limitations because to compile code, there are some things that need to be done. But we can see here a comparison if we're using the simple forward fill and backward fill of Pandas, or we implemented ourselves with Numba, and this is compiled. You can see this looks kind of like a C code, but it has the loops, but the code is compiled. So our code implemented with Numba is 3/4 of a time. So for a small operation, it can be very meaningful. And I think the last one is the model tuning, the last thing I want to talk about. And this is maybe comes up the best to the title of this talk, of latency and accuracy. So picking the right framework, or compressing our model, or even initializing our model better can really improve the runtime. So in this project, for example, we used a model that has initialization of some prior values. And when we just passed this step and we used random initialization, we got much better performance without giving up our accuracy. And in our use case, it really improved, saved us 2 minutes, which is very meaningful in our time span we had.
Okay, my name is Boris Rabinovich. I'm from Gilli's team. I would like to introduce our architecture for ML trade-off. Now it's better? Yeah, cool. So I would like to introduce our architecture to ML trade-off selector between accuracy and latency. So this is we have on the left the input to the platform, the set of time series, and then we have the metadata. One step before this, we have the admins. They can set up manually per each time series a different flow. We have 4 flows. The first one, intermediate, accurate, and most accurate. I will elaborate more just now. As Gilli mentioned before, we have 30,000 time series, and we have different time of cycles, minute cycles. Okay. Okay, so we have different minute cycles of our, when I mean the minute cycle, it's a full training set and prediction for all the time series. Okay, yeah. So if you would like to finish the full cycle in 1 minute, so we much care about the latencies and the accuracy. So in this case, we would replace more naive model like a seasonal naive model, which if we will in data, daily data. So it's just taking, for example, would like to predict the next Sunday. So we'll take the previous Sundays that we have in our historical data. So it's very fast one, and naive, we less care about the accuracy, but much more about the latency. Then if we have a 15-minute cycle of data, so we have more time, and we would like to increase the accuracy of our models, and again, keep the latency. So we applied the whole winter approach with we tried both approaches when we would like to optimize our starting point, like Sagy mentioned before. We tried both ways. If we like to, if we have stronger hardware, so we can optimize the starting value as well for the trend seasonality and the level values. If you don't have, we have less hardware, so we just disable this option. Then additionally to just providing the prediction points, we are adding the intervals. So it's additional computation. So if you have the time for this, and this 50 minutes we have, so I added this also. I will explain this a little bit more in the next slide. When it's applicable, we also try to optimize the latency as well. If you have a time series that's a relatively static one, so instead of retraining this every time again, so we just recognize this static time series and we just predict the actual values that we have before. So in other words, just a naive model. Then if you would like to increase accuracy more, for example, have aggregation of 30 minutes, so we can we increase the, we would like to increase the accuracy and become less care about the latency. So we have ensemble of univariate models like Walt Winter's theta models, the ones that won in the M3 time series competition, Prophet, NeuroProphet. So we run an ensemble of these approaches, which generates more accurate results and also have time to generate prediction interval. And the last flow, we just want most accurate models who do not care at latency at all. For example, we have a weekly cycle. We have a full week to train and predict. So we're applying deep learning based methods and also generating the prediction intervals. So again, we have on the left the set of time series data, the metadata, the admin set up before. Okay. So we have the set of time series data, the metadata that then the ML selector has these both tables, and per each of the time series, he knows where to route the time series to the fastest, intermediate flow, accurate one, or the most accurate. And then we're storing the data, in our case, to Kafka that the product can consume. Is this in another slide that this doesn't hear about? Don't have time? Okay. So just to summarize, Gilli spoke about the assessment metrics for ML project. Sagy mentioned the tips and tricks to improve latency. I spoke about the architecture to trade-off selector between the accuracy and latency per each use case. And as already mentioned before, you're welcome to join our Amdocs data science teams. Questions?